So now we're going to have a quick look at using locking methods or synchronization methods within free RTOS, so namely semaphores and mutexes. So if we look, firstly it's semaphores used for synchronization. A simple way of using a semaphore is just to get one task to trigger another task, right? And so I'm just going to comment out, this is the code from the last example, comment out my task 3, so it's just not getting created. And now in task 1 we have a delay of 1. Meaning that it's just going to come through, it's going to block on this. So if we run, for instance, or if we were to look at the states after this line, we would see that it's gone into a block state. Now, well actually there's a really nice, easy way of doing this. So if we go into the tasks, sorry, the libraries, libraries, kernel, into tasks.c, where we have our tick line. Oh, sorry, no, it should be in the port.c, tick line. Here, we can include at the top this function that prints out the task states that we saw in the first example. So we'll just include that, include, what was it called? TUM, can't remember, let's have a look what it was called. In here, and it was called TUM free RTOS utils. Go. And the function I'm after, so actually we'll keep the tick, and it was called TUM F utils. TUM F util print task state list. Util print task state list. So now every tick will see the states of the task being printed. But this doesn't look right, I don't have this code in there, so we'll just make clean, remove the cache, run cmake, run, make, and then rerun the code. This looks better. And so we'll see, I'll just put in a call at the beginning. So essentially, when the tick starts, we have this increment tick here, which we actually see this is when the tick happens, and then we'll show what happens after the tick here. So this way, when we'll see, for instance, sort of this before, or we'll make it even clearer. So we'll say print f before tick. After tick. There we go. So just for demonstration purposes, this should make it a little clearer when we're trying to figure out all the different states that everything's going into. So going back to our main code, let's have a look and see if we can sort of piece together what's happening here. Hello from task 1, hello from task 2. So we'll just clear this and run it again briefly. So we can see, we can start in here, hello task 1, what's happening? Task 1 and 2 are blocked. Yeah, it makes sense, they're coming in. Task 1 is saying hello, although to be fair, I should probably, we'll start from here because this is the init code and some weird stuff happens at the beginning. So we'll have here, so this sort of before the tick happens. So task 1 starts and task 2 starts. And so we come in, we hit hello task 1, hello task 2, and then they both block, which we can see here. They're both in a block state. Idle task is running because it's always running, right? And so this makes sense. We're in this state here. So then tick happens, which is this actual sort of like, it increments the tick, it checks, hey, what's blocked, is anything finished, can we put back into the ready state and get run? And we can see that then they're put back into the ready state and they run again, right? So this makes sense. This is what we've seen in the last example. But now what we need to do is, for instance, we can say, we'll use a semaphore to trigger this unblocking of a task. Like it will no longer just wait for this sort of time and this tick increment, it will now wait on a signal. And so what we can do is use the semaphore API, which was semaphore handle. So semaphore, and this will call this my signal, or my sync signal. Now we'll create it to null, because the good thing about creating things to null is that their actual creation functions, if they fail, then we can check that it's null, and we'll know, or like at any point in time, you can check if a handle is null, and if a handle is null, it means it hasn't been initialized or it failed to initialize and we shouldn't use it. So this way it's really handy. You can sort of say, before you use a semaphore, you can actually say like, if my sync semaphore here, sync signal, so this means if it exists, meaning it's been initialized, then I can take it, right? So if my sync signal, X, so we'll, for instance, say here, take you, put you here, X was semaphore take, where are you? Take here, block time. And so we're going to say, okay, we want to take it, and we'll say it's on my sync signal, and we're going to block for, I think it's port max delay, which is essentially indefinite. I think it's the max value of like whatever the port offers as its max value. On my system, because it's 64-bit, it's probably a 64-bit value, so the max value of that, which is going to be some, for all intents and purposes, indefinite amount of time. So we can say, okay, cool, if the signal exists, like if the semaphore has been initialized, I'm going to try and take it. Now if we look at the documentation really quickly, so if we look at, so close you, free RTOS API semaphore. Or here even better, X semaphore take. We can look at the return function, and so this is one useful thing, is that we know that it returns PD true if the semaphore was obtained. So what we can actually do is we can put this inside of a conditional and say if X semaphore take equals PD true, is it capitals, PD true, then we know it's been obtained successfully, right? And then we can say, we'll put this in here, right? And so otherwise we don't really do anything. So I mean, you could also, for instance, in here do some sort of like else printf couldn't take semaphore. But this shouldn't ever really happen as far as we're concerned designing this system. So, oh, this is going to complain because if the else could belong to this if, so we'll put this here, and there we go, we solved our vague structure. So now we can say, okay, so this demo task 1 is now going to block waiting for this sync signal. So if we run this, we'll see here task that task 1, if my sync signal, oh, we haven't created the sync signal yet, so this is what's the problem, is that it's not running this loop code here because my sync signal doesn't exist yet. We need to actually create that, and we'll do that in our main loop. And so we'll just say my sync signal equals semaphore order, what is it called, equal create semaphore binary, no, wait, create binary, yeah. So if my sync semaphore equals null, return or -1 because this means that it's errored. So now, was not guarded by an if statement, fix you up. There we go. Better. So here we can see that we have task 1, So the state, I'm not sure why it's an S, the suspended, essentially what it's doing is it's blocked, is that we can see that task 2 is running. This is fine, it's going to block because it's got its delay function here, here, and then it's resuming again, and it's printing, and it's blocking, but task 1 is just in the suspended state, right? So it's not getting scheduled because it's blocked on this signal. Now, I'm not sure, like I would have assumed that it would register as a block state, but it's the same thing. It's not available to be scheduled onto the system. And so what we can do to wake up this task is that we can actually give the semaphore. And so we can see here, for instance, we can go semaphore give, and I think here, and we want to give my sync signal. And then if we run this, we'll see that task 2 executes and then task 1 executes. Because task 1, it doesn't ever show it before, but why is this in this S state? This makes no sense. But what we can see is that the task 2 is running and then task 1 runs because task 1 gives this semaphore signal. And so this is evaluated on the next tick. So maybe we need to put in some more of these print statements to make it a bit more sort of visible. And so what we'll actually do is I'll take this and put this at the end of the tick, which would be here, like the proper end of the tick. So I'm assuming we're just not resolving some sort of I'm still quickly trying to figure out where I can place a print statement to show this well, all the states and how it blocks and unblocks, but I figured out why there's an S there and why it's suspended, because if I read the documentation, it says that if a block time of port max delay is specified, it will cause the task to block indefinitely, and also this task suspend, if we go into this and look at it, essentially means that the indefinite block is not actually putting it into the block state, but it puts it into a suspended state, which functions very much in the same way. But now to figure out a good place to put my print statements to have a good example. So now I've gone for a bit of a simpler approach, and that is that I have just littered the two tasks that we're looking at with some sort of printing the states. So we have our task 1 here, which is blocking, waiting for this semaphore, and we have this task 2, which is giving the semaphore. Now if we look at these print statements, so if we'll just make and run this, then we'll see we have the period of 1 tick, which is what we're really sort of interested in. We have this before give, and so what's happening here is that we have the state 2 is running, obviously we're in task 2. Then we have our task 1 in a block state. It's suspended because of, as I explained, there's this sort of like, if we're indefinitely blocking, it goes into a suspended state. So we have task 1 as blocked. And then we give the signal, and then we say hello from task 2. And then if we look at it, this signal itself, by giving the semaphore, we've returned task 1 into a running state. And so into a ready state. And so what this means is when the scheduler is next invoked, it can actually just say, okay, cool, let's go through the list of states that are ready and let's pick the top one. Maybe it'll be task 1. In this case, it will be. So we'll see here that after this call, we go up to hello from task 2, because now this call has been successful. We've obtained the semaphore, we've unblocked, and we're now saying hello from task 1. And as you can see, task 2 is blocked, which makes sense because it hit it's gone back up and hit its block statement on its delay. And so then we say hello from task 1. So this might be a little sort of convoluted, but we can see, for instance, if we just make everything really simple, that we're just giving the semaphore from task 1, from task 2, and we'll make it even more simple and put this one at the bottom. And that we are invoking the execution of task 1 from task 2, which makes it super simple, right? And this is how we use it for synchronization, and this way we can guarantee the execution order of certain tasks. So this is one use for semaphore, and this is pretty much the most common use for semaphore. Now on top of this we have the task notification, which we'll come to a bit later, because it's sort of like a semaphore, but it also involves transferring data, and therefore you'd say it's more of an inter-process communication. But we also talked about the mutex. Now the mutex is used for locking a shared resource, and so now it also uses the semaphore handle. So we'll say my resource lock equals null, and then before I forget, I will go and create it. So down here, my resource lock equals, and it's just mutex creates mutex, yep. And so we can actually take him down here and put in if my resource lock will return -1, because that means that it's failed, and yeah. So now let's think about when we would, oh, this is a colon, when we would need a lock. And a common sort of, I don't know what the words for it, like a common programming practice when you're using locks to lock structures or to lock a variable is that you put both of them in a struct, which we've been introduced to in the C programming exercises, such that it's very implicit which lock is responsible for which variables. And so we're going to do this now. So we'll make a struct, my struct, and we'll create a semaphore handle. So I'll actually put U in here. And then we'll create, oh, I can't put the null. And then we'll put in here a variable. So int my variable. And so then we'll create struct instance. And what we'll do is we'll use the initialization to make the lock equal to null here. So this way we're guaranteeing that our, my resource lock, will make this just called lock. There we go, and then we'll just change this down here to be, because we still have to initialize it, we've set it to null, so my struct instance dot lock, and so we're initializing the lock here, and then we'll just do the check now on this my struct instance dot lock. There we go. And so now I have a structure set up which has a lock inside of it, and it's initialized to be a mutex, so it's this sort of like take, use, give concept. And it's very implicit to anyone using or writes or like sort of extending my code that this lock is linked to this variable, because there's only two of them in a structure, and so generally if there's a lock in a structure, it locks everything within inside that structure. So anytime you want to use anything in that structure, you have to take the lock and then you give it back. So now what we can do is we can sort of set up a couple of different tasks to do this stuff, and what we'll do is that we'll now use task 3. So and if I want to access in task 2 and in task 3 the same data, what we need to do is we need to first take the lock. So in task 2 I'm going to try and increment the variable, this my variable, the integer here. And so the process of doing this is we also take the semaphore before. We use the same as here, right? And so there's a couple of different ways we can do this. We can say, the only difference really being the delay here. So we'll do it a couple of different ways. So we'll say x semaphore take, and then when the semaphore we're taking is my struct instance dot lock, and we can say I want to port max delay on it. And so if this equals PD true, then we've obtained it. So we know, yep, we have the lock. So we have the lock, and we can modify the structure. So now we can just say my structure instance dot variable plus plus. Right? We just increment it, and now we've incremented it. We have to give the structure, the semaphore back. So we're x semaphore give, and then we're giving my structure instance dot lock. Right? Now this has a permanent delay in it, meaning that this function, this task is going to block here for permanently, similar to this one, and it'll enter a suspended state if this resource isn't available. Now what we can do to sort of show this is that we'll do it here, and we'll just take the lock. We'll just go, just really semaphore take my structure instance dot lock, and we'll put in port max delay. But see, the thing is, we're taking it here, but we're not giving it back. So this, at some point in my code, task 3 will obtain this lock and will hold on to it. And we'll see then that task 2 will enter a suspended state and cease to function, or cease to execute. So we see hello from task 3, task 2, and task 1. Makes sense. Task 3 executes. Task 2 executes, then it runs this print statement, and then it's getting trapped here, right? And so if we print, for instance, the, so like, hold on, TUM, what was it, TUM F util print task state list. Sorry, we need to hello time from task 3. We'll put this here, and we'll put it here. So we can see they're all running, all happy, and then hello from task 3 hits, and then task 2 and task 1 are obviously hitting suspended, because task 2 is suspending on this lock, and then task 1 is still suspending on this signaling semaphore, right? So this is the problem that we hit, is that essentially here nothing else, like task 3 has taken the lock, and then it's going to try and take it again, right? Because it doesn't know that it owns it, it's just going to try and take it again. And so this is the problem, is that we've hit essentially what is a deadlock. Like, as you can see here, we're ticking, but nothing's actually being done. Our program is just ceasing to function because we've not given back the lock. And so therefore we need to resolve this. And so how we can do this is that we can do a similar thing here. We'll put in if statement, and we'll give it a 0 delay. Or actually, hold on, one good way is that we can just put in here if was it port true? Yeah, no, PD true. And so here, by doing this if else, which will make it a bit neater, we have in here is only gets executed if it gets the lock, but it's not going to block. It's going to try and get the lock, and then it's going to keep going. And so this gives us a bit of extra functionality in that it doesn't cause the task to stop, but we can sort of say, hey, we're going to run this code. If it can get the lock, do this. If it can't, keep going and do this. It's not going to cause it to block him permanently. And so here we can just, for instance, take him and put him here. And so now we can see that it's running, it's printing the states inside of task 3 because this else statement here. The first time task 3 ran, which we can see here, it's saying lock obtained in task 3, but I'm not giving it back. And then every other time it fails to get the lock, and so it prints out the lists here. And so it just prints out the states, and we can see that task 1 and task 2 are still suspended. Now, what we should do is that we should, in here, go x semaphore give my struct and everything's happy again. Lock obtained, and then task 2 keeps running because it can also get the semaphore lock, which we've given back. And so that's how a lock is used. We take and we give it. So hopefully this makes sense.